Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. Welcome to this video on Vlsi Semiconductor Fabrication Technology. In this video, we will overview the semiconductor wafer, device processing, fabrication, parasitic, yield and other related issues involved in the manufacture of very large-scale application-specific integrated circuits. The VLSI design methodology is a structured process that guides the design to realizes a very large-scale integrated circuits. The simplified flow diagram shown provides an overview of the key steps involved. Design specification file defines the required chip functionality and is inputted along with the design constraints. Logic design operation, also known as front-end, translates specifications into a bug-free hardware description language code that is simulated and verified for its functionality. Synthesis is a process of mapping HDL code onto the targeted technology library gates. Physical design operation carries out floor planning, placement and routing of gate-level netlist onto the physical library gates. Physical verification ensures that the layout meets the fab defines design rules. The physical design layout created is then passed on to the fab for fabrication. Fab sorts out the layouts into a set of different material layer masks, which are sequentially used to create patterned material layers. A set of active layers form the devices and the overlapping metal interconnects are isolated by isolation layers. This structure forms an ASIC that electrically implements the required functionality. Semiconductor device fabrication starts with growing a predefined resistivity and orientation silicon single crystal that is sliced into wafers of required thickness. On the wafers, using physical masks and semiconductor processes create various patterned material layers. The overlapping active and interconnecting layer structure realizes the required functionality. Processed wafers are then tested, sorted, scribed, mounted and packaged to create a finished ASIC. By employing different semiconductor processes, patterned material layers are created or removed over the starting silicon substrate. Semiconductor device processing is carried out in clean rooms of controlled particle sizes. These clean room environments are strictly controlled for temperature, humidity, gases, lighting system, airborne and human contamination. The materials, jigs, fixtures, processing, test and monitoring equipment are remotely controlled by automated systems. Photolithography is a crucial part of a semiconductor fabrication process, which is repeatedly carried out in creating a multi-layer chip. This process uses photoresist material to transfers a physical mask pattern onto a chemical mask and creates different patterned material layers. Photoresists are of two types, namely positive and negative. Positive photoresist by default is acid resistant and on exposure to light dissolves in acid. On the contrary, negative photoresist by default is insoluble in acid but, after exposure becomes soluble. Some of the processes used for creating material layers are: ion implantation is used for doping, epitaxy for thin layers creation, diffusion for thick layers creation. Metallization, sputtering processes are used to deposit metal layers for pins, ports, interconnects, etc. Sputtering process is used for physical vapor deposition and is used to create thin film layers. Some of the processes used for removing material layers are: dry or ionic etching is used to remove fine layers of materials, whereas wet etching is used to remove thick layers. Mechanical and chemical polishing creates surface planarization, so that subsequent processes layers created are in one plane. Annealing process is used to restoring the device crystalline structure deformation that is likely to occur during processing steps. Ultrasonic cleaning removes adhesive and particle contaminants. Organic chemical cleaning removes impressions and the left-out fine residues. A thin layer of photoresist is coated on a silicon substrate and, through relevant mask, it is exposed to UV light. Depending on type of photoresist, it gets pulverized and creates the mask pattern. The exposed wafer is developed in acid, the unwanted portion is washed off and left-out material becomes a chemical mask. Further left-out photoresist, if any, is removed by stripping process. These series of processes steps are repeatedly employed in creating multiple material layers. The figure represents a conceptual structure of an ASIC die, made up of different layers, and are separated by isolation material. Typically it consists of active, interconnect, isolation, passivation, pins, contact, vias-like layers. Continuous innovations in fabrication processes and technique is increasing the layer count and enhancing the device performance. The primitive, only P or NMOS technology are associated with lots of limitations. The devices had higher threshold voltage, large leakage current, slower speed, higher voltage drop leading to higher power dissipation and temperature. These limitations are overcome by combined NMOS and PMOS transistors in the design, and is known as complementary MOS technology. A CMOS technology exhibits improved performance, lower power consumption, and higher noise immunity, but the structure is associated with latch-up issue. Twin well technology allows better control of the threshold voltage of both transistors, provides transistor isolation, reduces latch-up risk and enables use of higher supply voltages. SOI technology offers reduced parasitic capacitance, leading to faster switching speeds and lower power consumption, better isolation between devices and improved performance. A multi-die device involves integrating multiple semiconductor dies onto a single package and collectively implements complex functionality. Each technology has its own set of features and is selected based on the specific applicational requirement. Sequentially created, overlapping layers will undergo process variations in mask alignment and wear, doping concentrations, etching, thickness and uniformity, interconnect spacing and width, particle contamination, equipment calibration, etc. This results in batch-to-batch, wafer-to-wafer and spatial variations on a wafer that alters performance and yield. These variations are minimized by employing new processing methods and techniques, and a self-aligned process is one of them. In self-aligned process, the MOS transistor gate is first created and is also used as mask to create source and drain layers. This minimizes the gate, source, and drain misalignment and reduces inter-electrode overlap capacitances. In addition to improved yield and performance, new techniques create smaller, faster and more power-efficient transistors. The figure shows the cross-sectional view of a CMOS inverter that is made up of different material layers. Using various processes, layers are deposited throughout and unwanted portion are removed. These sandwiched layers are isolated by silicon dioxide layer, and overlapping layers form devices in metal interconnection form nets. The resulting structure is an integrated circuit die, which mounted on a package, forms an ASIC. During wafer processing, test dies are incorporated at different locations and are monitored for health. The wafers are tested and the rejected ones are inked to weed out. As the dice are square and wafers are circular, the silicon wafer is not completely converted into dice. In addition to processing defects, the peripheral dice are malformed and result in poor wafer to dice conversion. Yield is a critical parameter that directly affects the production cost. Market competitiveness, time to market, profitability, and brand reputation. The semiconductors are very capital-intensive and short life cycle products that demands precision, speed, and cost competitiveness. Some of the important features of the infrastructures are low particle contamination clean rooms, ultra-pure water, controlled environment of temperature, humidity, vibration, uninterrupted power supply, ultra-pure materials, programmable and remote-controlled jigs, fixtures, process and measuring equipment and material handling systems. The innovations, technological breakthroughs are regular features of semiconductor industry. Some of the advancements are creating high-density chip by 3D integration, FinFET technology for superior power consumption, extreme ultraviolet lithography for smaller feature sizes, innovation of new materials for better performance and efficiency, improved architectures, AI-driven algorithm for design optimization, advances in packaging techniques, etc. Thanks for your time. Hope this video has been helpful in appreciating the challenges experienced by semiconductor industry. Thanking you once again and hope to meet you in the upcoming video. Bye for now.